So far we have seen several methods that are able to do optimization on finite dimensional vector spaces, right? Like linear programming, we have an n-dimensional vector with several linear constraints, and we can minimize linear constraints on that. Then we learned about Newton method, and we learned about gradient descent and conjugate gradient and quasi-Newton methods and so on. They were all operating in finite dimensional vector spaces. And then we started to discuss semi-definite programming, where the inputs are actually positive definite matrices, right? We want to minimize a cost function that's a linear function of a positive definite matrix, right? So today we are going to continue discussing semi-definite programming. We will see a few applications why this is important. I hope it's still alive. Why it's important. And then we continue discussing other problems where we also want to optimize over matrices, but then our constraints for the matrices won't be that they are positive semi-definite, but they will be orthonormal. Okay, so we want to minimize functions over orthonormal matrices. Okay, that's the plan. And the application for that, for this last problem, will be independent component analysis. Okay, that's the plan for today. So let's just recap what we have discussed so far. So just to remember the notations, Sn is the set of symmetric matrices. The size is n by n. Sn plus is the set of PSD matrices. We proved a couple of basic properties of PSD matrices. Two important, right? Some important properties are that if we have a PSD matrix, then we can decompose this as QD, Q transpose, where Q is orthonormal, D is diagonal, and each entry is non-negative. And another property that we will use a lot, and we even used this last lecture, that the matrix X is positive definite if and only if all minors, so for example, this matrix A here, which is a symmetric n by n, if this is n by n, I don't know, k by k matrix. This is positive definite, and the Schur complement is positive definite as well, where the Schur complement is defined by this expression here, right? You remember that. And some special cases, you can also think of these constraints as when you know that the determinant of this matrix has to be positive, right? Because X is positive definite. So what would be the determinant of this matrix is A times C minus B squared, right? And you know that A is positive, so if you divide the determinant with A, then you would get something like this, right? So this is how you can remember, right? So the determinant is A times C minus A times B transpose B. You divide this with A. So this is just a hand-waving thing, but this is how you can remember the Schur complement. Okay, we introduced the inner product between matrices. And there was a theorem which says that if A and B, they are positive definite, then the inner product is 0 if and only if the product of these matrices is 0. After that, we defined semi-definite programming. And this was the primal form of semi-definite programming. We want to minimize the inner product between a matrix, symmetric matrix C and X, subject to that we have M of these constraints that the inner product between X and matrix AI is BI, where BI is scalar, AI is a matrix. And again, our constraints on matrices that X is positive semi-definite. We defined the dual problem as well. And it was the generalization how we defined the dual in vector spaces. So in semi-definite programming, this was the primal problem, how we defined, and this is its dual, that we want to maximize this objective in Y's, where Y is an n-dimensional vector, B is an n-dimensional vector as well, subject to this difference here is positive semi-definite. Okay, we also discussed that sometimes semi-definite programming is defined this way, so in the first definition, this was the primal, this was the dual, but you might find papers where they define this to be the primal problem. You want to minimize C transpose X subject to this expression where F0, F1, Fm, they are symmetric matrices, and this is a linear combination of these matrices. This is positive semi-definite. We proved that SDP is convex problem. Then we did this sketching that you can see that the SDP is like a generalization of linear programming, where in linear programming we had this polytope, we had a linear function, and we wanted to move this straight line parallel to the vector C, right, such that this line is, had extreme value. But the difference here is that you remember that with linear programs, we had a polytope here, which is piecewise linear, right? But now it's piecewise something either linear or curved. We also discussed that a little bit, that you can think of linear programs, semi-definite programs, as linear programs, but with infinite many constraints. And because you have infinite many constraints, that's why if I can have infinite many lines that would make it curve this polytope, right? Then we proved that linear programs are special case of semi-definite programs. And we also discussed one problem, one SDP that was not linear program. And this is where we proved last time. So now what we are going to do, we discuss some duality properties of semi-definite programs. Any questions so far? Questions? Everything is clear? Easy? Good. So I'm a bit worried that if I move this laptop, I will lose that one as well. because so far it has always happened to me. So let's see. So this is the primal SDP. Is we want to minimize the linear product between C and X subject to inner product between AI and X is some BI. We have M of these constraints, and X is PSD, right? And the dual of this SDD is we want to maximize B transpose Y. Y is m-dimensional, subject to this matrix C minus YI AI. Success?
Really?
No, I mean you any success?
No.
Oh,
Okay,
good.
so somebody will come look at it, but they said it's usually going to take a long time to fix.
Good. Thanks. So worst case, we will use Blackboard. So this is the dual. And we have the weak duality, which weak theorem says that the duality gap is non-negative. That is, if matrix X is feasible.
Excuse me.
Hello.
There's a report.
Right.
Sparks coming from the
So this one, it's completely black. These guys, I think they should be inside of this, and it's sparkling there.
Okay. So y'all still in here?
Thanks.
Okay, got it.
So
What time is this class over?
the class is over at 4:20.
Okay, is it all right if I try to fix this right now?
Is it possible that I can use that
Yeah,
one? Yeah,
yes,
that,
sir,
yeah, that would be
I'll
good.
come back after the class,
Okay.
but I'll separate them so they don't spark.
So X is feasible of the SDP.
Okay. So you want me, can I turn this off and raise it up?
Right, that's good. So I just need that one. YS is feasible of the dual. Then the duality gap C X minus oops. So minus the objective, right? That's non-negative. That's the weak duality theorem. Okay, it's complete analog of the LP. Can you see the proof? It should be same. It's exactly the same as we proved for LP. So what's the duality gap? Inner product between C and X minus B transpose Y. Oops. Okay, and so what's the next step? I need your help. Yes? Let me go there. Which one? Oh, sorry. Yeah. S is this difference here. Thanks. Okay. So C minus this. That's S. That should be PSD, and Y is just a vector.
It's mostly just conditioning on Y.
You're conditioning on S only, right?
It only depends on Y, right? Y is the only thing that's going to change. A is fixed, C is fixed. So
Right.
really Y.
Right. Y is what you optimize. It depends only on Y. It's a vector. and but the constraint is on S. Good point. And yeah, that's a good point here, because if you think, later we will discuss how to solve, so what are good algorithms to solve this. When we think of this primal, we want to optimize in a right? Our variable is a matrix. But here actually it's a vector. So sometimes it's easier to consider this problem because again, you just optimize over a vector. And when we have matrix, the problem is that you have an objective that's a function of a matrix. The gradient of that, it will be a matrix. But the second derivative, what would be that? Right, it will be like an ugly tensor, but still everything is manageable. It's just a bit more of a headache, right? So sometimes people like to work here. Okay, so, but to answer my question, what's the proof here? Yeah, exactly. So we know that this is AI, inner product between AI and X. Right? Next step. Right. So C minus, I move this yi inside, everything is linear, and yi is just a scalar. Right? B is a vector, bi is its ith component. So B is a m-dimensional vector, bi is a scalar. So I just, yeah, so this is B transpose y. Okay, someone please finish the proof. Right, so this is S, which is feasible, so it's PSD, this is PSD. So the whole thing is non-negative. Good? Right, so we had this property, if we have two PSD matrices, then its inner product is non-negative. Okay, so the next question we want to discuss, what happens if the duality gap is 0? So we proved that the duality gap is non-negative, right? So that so we have the, I don't know, primal dual. I don't repeat it. And the theorem is that if the duality gap is 0, so if this was the duality gap, then you can prove that X is optimal in SDP and YS is optimal in the dual SDD. And you can also prove that the duality gap, right, so this is, I mean, this is trivial. This is S, so the inner product between S and X, that's 0. But from this, it also follows that S as a matrix times X as a matrix, that's 0 as well. Okay, so duality gap is always non-negative. If we reach 0, then they are optimal. So nothing surprising happened so far. But now there will be something surprising happen. In semi-definite programming, it might happen that you will never reach this zero duality gap. And this can happen in two different ways. Here is one. So in semi-definite programming, it might happen that infimum I'm thinking which variant should I write to you. So let me rephrase this with the dual. It's easier. So I could write this dual with instead of maximizing something, I could write it that, hey, let's minimize the inner product between vectors. So it might happen that, say, infimum C transpose X, this is finite in SDP, but actually there is no X that achieves the minimum. So again, in SDP, we have objectives, right? We want to minimize the objective. And how we formalize that, say, minimize B transpose Y, C transpose X, doesn't matter how I write. You want to minimize that. Say the minimum or the infimum of that would be 1, but there is no X with which you achieve that infimum. Can someone explain to me why? We will see a concrete example for that, but why it can happen? So with linear program, it didn't happen. If the minimum, we could always achieve the minimum. So there was always an X. So the objective of a linear program, say, minimize C transpose X over X. If the infimum is +1, we can always find an X such that that achieves this infimum. Right, because the feasible set can be open.
So you keep going towards the boundary but never touch the boundary because it's not there.
Right. So you remember that. So it's a convex problem, right? You remember this example where we were talking about convex sets and touching hyperplanes. And say I want, this is say 1 over x. This is convex. I want to minimize, and say this is my C vector. This is C transpose x. I want to push this till I reach this. But it would reach this 1 over x set in the only when x is infinite, right? So, but let's see a concrete example, and then it will be more clear. So let's minimize x1. We will have two variables, x1, x2. And the constraint is subject to that this matrix, this is PSD. So I can rewrite this to look more familiar to you, that this is the same problem as let's minimize x1. Two variables, we have x1, x2, subject to x1 times, what's the matrix? 1, 0, 0, 0 plus x2 times, any help? 0, 0, 1 plus, right, 0, 1, 1, 0. This is PS. This is non-negative. Right, so this PSD problem, now it's exactly in this form how we defined earlier somewhere. Oh, that was in the PDF. So you just, sorry, you have to remember. Anyhow, so this is our problem. This is a PSD problem. So what's the minimum of this? Let's solve it. What's the minimum? Right, I cannot hear you. What's the minimum? Right, so the minimum will be 0, right? Why the minimum is 0? Because x1 cannot be negative. Why? Because this guy here has to be non-negative, right? So the minimum is 0, x1 is 0. But the problem is that x1 cannot really be 0 because we have another constraint, that is x1 times x2 minus 1 is non-negative, right? The determinant of this matrix, it's a 2 by 2 matrix, it has to be positive because it's PSD matrix. So x1 times x2 minus 1 has to be bigger than 1, which means that x1 cannot be 0. So the minimum of this SDP problem is 0, but there's no the x1, x2 that actually achieves that. Everyone is fine with this? Who got lost? So this is clear, right? Good. So we have strong duality theorem still, which says that let x be feasible of the SDP. Ys feasible of the dual. And now let x be strictly positive definite, so not just semi-definite. And let this S be strictly positive definite as well. And then you can prove that, say, if Z, I don't know, P star is the optimum of the primal, optimum value, and say Z star D is the optimum of value of the dual. So if we have these two extra constraints, then you can prove that the primal and dual optimum, they are the same. So the duality gap is 0. And what's more, these can be attained. So the infimum is the minimum and the supremum is the maximum. In other ways, you can find really an x that achieves the infimum in the objective, and you can find y and s that achieves this optimum as well. Okay, so in this example, so this was an example where the infimum is not the same as the minimum. So now we will see an example where the duality gap is finite. Okay, so with the strong duality theorem says that if these conditions hold, the duality gap is 0. But we can create some weird examples where this duality gap between the primal and dual problem, it will be finite. So it's something, again, that's something new that you haven't seen with LP. With LP, the duality gap always was 0 or infinite. So here is the example. So this is the primal problem. Let's minimize x1. This is our objective. Subject to this matrix x1 plus 1. This is PSD. So in other words, I can rewrite this again as x1 times plus x2 times 0, 0, 0, 0, 1, 0, 0, 0, 0, plus what is C? The last constant matrix. What should I write here? 1. Thanks. Okay, so this is our primal problem. But let's calculate its dual. So let the primal be defined as this, that maximize x transpose B. X is a vector, subject to C minus 1 to 2 xi ai. This is PSD. Okay, so this is a primal problem. This is the primal problem. This is our problem on the left side. So tell me what's vector B. So what's B1?
You mean max or you mean min?
I mean max here. Right, so so the problem that it doesn't matter, right? Sometimes people say this looks like a primal. Sometimes they say this looks like a dual. It doesn't matter. It's let's now say this is the primal and what's the odd dual. Or if you want, you can call this dual and then tell me what's the primal. Okay? I mean, it doesn't matter. If you just start from one and you derive the other. Okay, but the problem is, so now we have this, so this is our problem. That's clear. And there's one version of SDP that looks like this. Let's just call this primal for now. If you want, you can call it dual, doesn't matter. The question is, what would be vector B in this case? So we want to minimize x1. And I want to rewrite this as x transpose B. So what's B if x transpose B is x1? Right, so first we have to rewrite this maximum to minimum. Right, so that's why B1 is -1 and B2 is 0. Right, so it's then in this case, we want to maximize minus x1. That is, we want to minimize x1. So we are good with that. And what will be matrix C? So now we are looking at this, and I want this constraint here to be the same as this one. So what's matrix C? Is this, right? And this will be minus, thank you, minus A1, and this is minus A2. Okay? So the dual problem is we want to minimize, now this is in this form, subject to okay, so let's see how does that look like. So we want to minimize the inner product between C and Y. That's C and Y. We want to minimize this in Y. Subject to, we have two other constraints, right? AI, the inner product between A1 and Y is B1, and the inner product between A2 and Y is B2. So B1 is minus 1, I can multiply, and this is minus AI, I can multiply everything with minus 1. So what we have is that subject to this is 1. And there's another constraint that the inner product of A2 and Y, that should be 0, right? Okay, so what is this expression? So we want to what's our objective? We want to minimize this. This is just Y33. What is this expression here? The constraint Y12 plus Y21 plus, there's one here, Y33, that's 1. And from the last one, we have that Y22, that's 0. Okay, so this is our dual, and of course we have that Y is PSD. Okay, so let's see what we have done. So our primary problem was to minimize x1 subject to x1, x2. This is PSD. So what are the feasible primary solutions for this? How do they look like? So what do we know about for x1? So we know that this matrix is PSD. How, what values can we allow for x1 for this matrix to be PSD? No, so when is a matrix? So we had this property for a PSD matrix. If a diagonal is 0 in a PSD matrix, then what do we know about the rows in that? Yeah, everything is 0. So if in a PSD matrix, it's called the diagonal matrix is, the PSD matrix is always diagonally dominant. It means that the diagonal element has to be larger than the absolute values in that row. As a special case, if the diagonal element is 0, then everyone else should be 0 in that row and that column. So we have this diagonal element is 0. It means that x1 has to be 0. Otherwise, this matrix won't be PSD. Okay? So we know that x1 is 0. We have 0 here, 0 here. What do we know for x2 now? So in the row of x2, we have zeros, and in the column of x2, we have zeros except x2. How can it be PSD? So x2 has to be non-negative, right? Our cost function is we want to minimize x1. So the primal optimal will be 0. x1 cannot be smaller than 0. Okay, what's the dual? We want to minimize y33. In other ways, I want to maximize y33 subject to, we had this constraint and this constraint. This is 1, and y22, this is 0. And we also know that y has to be PSD. So the question is, what are the feasible dual solutions for this matrix y? So we know y22 is 0. What does that imply? Again, that it implies that the second row and second column is 0. Okay, now we have this constraint as well, that y12 plus y21 plus y33, that's 1. What is y12 and y21? We just calculated, they are zeros. Right? y12, this is this guy, y21, this is this guy. So from that, it follows that what's y33? It's 1, right? And say we have some value a and b here. So what's the dual optimal value? Is 1. So what? Right, minus 1. Good point. Right? So what you can see that the primal optimal is 0. Dual optimal is minus 1. So there's a finite gap between them, although they are optimal. Isn't it a contradiction to our strong duality theorem, which says that the duality gap is 0? Right? We had that duality gap is 0. And we found an example where the duality gap was 1. I'm a cheater, right? So what went wrong? Right. So there has to be an x and a primal feasible and a dual feasible where they are strictly positive definite. But if you look at the feasible solution in our primal and our dual, it turns out that the determinant will be always 0. So they will never be strictly positive definite. Okay? So let's have a few minutes break and we continue from here. So we have seen a couple of properties of SDP semi-definite programs, and now let's see a few applications. So why this is useful. And one famous application is called the max cut problem. where we have a matrix G. We have a graph G which is undirected. It has a node set N, and it has an edge set E. And let's assume that Vij is a weight on the edge from I to j. And the goal of the max-cut problem is to find a subset S. It's a subset of the nodes. Its complement is denoted as this, such that the sum of the weights of those edges that are going from S to S bar, that's maximized. So if we have a graph somewhere here, and this is set of nodes S, and then we have S bar outside of S, and say these are the edges between these two subsets. We want to maximize the sum of these weights. Is it clear, the problem? So formally the problem is that, say, let xj be 1 if j is in set S, and let it be -1 if j is in S bar, the complement of S. And now what we want to do is, in the max-cut problem, to maximize where x, the sum subject to so it's xi times xj. Why? Because if xi and xj, they are in S, then this product will be 1. If they are both in S bar, the product will be 1 again. So this 1 minus xi times xj, it will be non-zero if and only if this is an edge from S to S bar. Okay, so this is what we want to do. It's an integer program, and this is NP hard. But with semi-definite programs, we can relax this integer program, and usually we can find good solutions. So let's see how to do that. So again, this was our problem. So let's introduce this notation that Y is a matrix X times X transposed. So it's a symmetric N times N matrix. So in other ways, Yij is Xi Xj, right? And now I can rewrite this max-cut problem such that let's maximize So let's decompose this. This is Yij minus sum double sum Yij xi xj. And what is this expression? If I want to use this matrix inner product notation. Yeah, this is the inner product between W and Y. And our constraints are that xj is in this set and y is x times x transpose. So one observation we can make that I can rewrite this constraint, this one, just saying that Yjj is 1. So if y is x times x transpose, and we know that xj can be -1 and 1, it's the same as saying that y is x times x transpose, and the diagonals of that y, they are all 1s. Okay? So this is where we are now. We want to maximize this subject to Yjj is 1 and y is x times x transpose. So now what we want is to relax this with a SDP problem. So what should we do? How can we relax this with an SDP problem? So this is not semi-definite problem yet, but what should we do?
Is this still the exact problem? Because I can imagine there will be other x's that would lead to the constraint.
So it's still the same, right? So because of this. So y is, so if y is x times x transposed, and its diagonal is all ones. So it's a rank 1 matrix with all ones diagonal. From this it follows that x has to be, all elements of this vector x has to be -1 or 1. So it's still the same problem, but it's not an SDP yet. So any ideas how can we make it to be an SDP? So why is it not an SDP? What is that constraint? So the objective looks like an SDP, right? I want to maximize this in y. Y is so by the way, here, if you look at this, with these constraints, from this it follows that y is positive semi-definite, right? Y is x times x transpose. So it's PSD. So our objective looks like what we have in semi-definite programs.
You make y matrix -1 semi-definite?
Right, so this is our objective, right? Max over y. And we have these constraints. I want to relax this in such a way that what we will get, that's an SDP problem. It won't exactly solve this. So the objective that it's all fine with us because everything is like linear in y. But the problem is that the constraints what we have is yjj equals 1. That's not a big issue because they're still linear in the elements. But then we have this rank 1 constraint. And that makes this whole problem not an SDP. So what we do that we just forget about that and we just write that y is PSD. And you can, it's still a bit ugly, but from this homework, you can check that you can rewrite this in one of those primal or dual problems. That's what we have. So this is now an SDP problem. What we did, we just forget that rank 1 constraint. So if we optimize this, where the diagonals are all 1 and y is PSD, then it will be a relaxation of the original problem, but quite often it gives good enough result.
Suppose we get a solution y star, and we factorize it into another x star transpose. There's no way to guarantee that the single entries of x will be -1 or 1.
So yes, so what we can do now is it will just give us a bound, right? So that's all we can say, that the max cut optimum value, this will be less than this relax value. That's all what we can claim. But at least we can give some bound on a NP-hard problem. Okay, so let me just state 2 more interesting statements. So we discussed that the max cut problem is NP-hard, right? It's also NP-hard so it's very difficult to find the optimum value of the max cut problem. But it's also NP-hard to find a cut with more than 16/17 max cut edges. So you can prove that too. So not just that max cut is NP-hard, but this is NP-hard too. And you might wonder, what's that? How much I can reduce this to be NP-hard, and when is that value when it becomes polynomial? And there's a result which says that it's polynomial to find a cut with at least something times max cut edges, and I'm curious about your guess. Oh, someone already know. So it's the best result so far is this 0.878. So it's pretty close to 0.94. And for me, it's just interesting that with 0.94, it's NP-hard, but with 0.878, it's polynomial. The statements are clear, right? So another application I want to discuss is called quadratically constrained quadratic programming. So we have a we want to minimize f0x subject to fix is non-negative we have, say, L of these constraints, where f0x is a quadratic function. Let me just say all of them is a quadratic function. X is okay, these are convex quadratic functions. So your objective is a convex quadratic function, and your constraints are convex quadratic functions as well. And I claim that we can rewrite this problem as an SDP. Is it trivial or not? But you can see how useful this is, right? That now, from now on, if you want to minimize a quadratic objective where you have quadratic constraints, then if you have a SDP solver, then you can go ahead and solve it.
Why are you using that one, like, complex form of AIX plus BI and so on? Like, we could just say X transpose QX with Q.
Right, good point. Because how I rewrite this to an SDP, it helps a little to that. But indeed, we could just say, I mean, it could be like X transpose Q X plus B transposed X plus constant, right? But we have to be careful that this Q has to be convex. So I mean, this Q cannot be anything. That's my point. Okay, but if it's in this form, this is always a convex quadratic problem. And the key step here is that this is non-negative if and only if you can prove that this matrix here this is PSD. Can you see it why? Right? Sure complement. Right? So this is cool because we had this ugly quadratic constraint, and now we have SDP constraint. One problem, though, is that we have L of these constraints, but we can just stack them together to have a large semi-definite problem. Oh, and there's another problem that our cost function that's quadratic too. And in SDP we had linear objectives. So what can we do? We did that trick before. That if you have an ugly objective, you can always move that to your constraints. And you can replace that ugly objective with a linear objective. So now our objective is quadratic. We can move that to our constraints, and we will have a linear objective where all the constraints are quadratic, and we can use this transformation with them, and we will get an SDP problem. Do you remember what that trick was? So we have a ugly objective with some constraints. How did we rewrite this to have a linear objective? So we wanted to minimize a t, say, subject to the original constraints and f0x smaller than t. Okay, so this is the trick how you can rewrite convex quadratically constrained problems to SDP. So here is a question. So we don't have time to discuss now, but you can also prove that you can solve SDPs in polynomial time. So that's a good thing. We can solve these problems in polynomial time. So what happens if this QCQP problem wouldn't be convex? So what do you think how difficult then that problem is? So we have seen that if this is convex, right, we can rewrite it as an SDP, and we know that we can solve an SDP. SDP is a convex problem. We can solve that in polynomial time under some very mild conditions. What happens if we have a quadratic problem with quadratic constraints, but they are not convex anymore? So what do you think how difficult this problem will be? The question is clear, right? So if we forget that they were convex quadratic functions, we just have quadratic functions, quadratic objective, quadratic constraints, how difficult that problem will be. Okay, so the answer is that it's NP hard. And it's very easy to see, because integer programs are special cases of this. So if you have integer constraints, 0, 1, I can just rewrite these constraints as this is 0. And I can rewrite this as bigger than 0 and smaller than 0. And this is quadratic constraint. So I can rewrite any integer problem as a problem with quadratic constraints, but these quadratic constraints are not convex anymore. Okay, we really run out of time. There are many more applications of semi-definite problems. You can use this for eigenvalue optimization, find the maximum eigenvalue, for example, or if you have a set of points and you want to find the smallest ellipsoid that covers that set of points, that's also an SDP. And there are lots of other combinatorial optimization problems where you can either rewrite the problem as an SDP, or at least its relaxation of that problem is as SDP. So there are lots of other applications. We didn't have time to discuss how to solve SDPs either, but let's just discuss them in 10 seconds. So SDPs look like linear programs. So what kind of solutions we had for linear programs? We had simplex method. Can we solve SDP with simplex method? No. So that's no good. But we had ellipsoid method, and we had interior point methods for linear programs as well. And you can solve SDPs with those methods. The derivation is exactly the same how we did for LPs, just a bit more messier, uglier calculations. Some of the details will be in the slides. I can give you more references if you want to look at. All the results theory, they are very analog to what we have proved for LP. So I think I've finished SDP for now. We don't have more time to discuss them. And we didn't have time to start what was the topic of this lecture, is matrix differentials. So I will try to ask Ryan to steal some of his time and discuss those things. And but that's after midterm only. Okay? Oh, we could do that too. That while you write the midterm, I could present still something. Save some time. Okay, so have fun.
Would you like to sign kindest birthday card for Junior.
Sure.